This is the Unit 4, Section 3 EdPuzzle quiz on the ideal gas law, and a little bit of earlier gas laws too. First, let's talk about the general properties of gases. Gases have a lot of free space between the different molecules, and they can expand infinitely to fit their containers. They do fill those containers uniformly and completely. They also mix rapidly. If you put two gases in the same container, they will mix together. Now, we talked about three early gas laws and did a little bit of math with them. We talked about Boyle's law, which said that as we increase the volume of a container, the pressure will decrease because those particles don't hit the sides of the container as much. We talked about Charles's law. As the temperature increases, volume increases. Think about a balloon expanding in hot weather. And Gay-Lussac's law, as temperature increases, pressure increases. As those particles move faster and faster, they hit the walls of the container more often, increasing the pressure. So for the first question of this EdPuzzle quiz, let's say you have a gas in a container. It's got a pressure of 1 atm and a volume of 2 liters. What's going to happen to that pressure if the container is squished and the volume decreases to 0.5 liters? Go ahead and answer that question now. You should say the pressure will increase. If you squish a container, according to Boyle's law, when volume increases, pressure decreases, and the opposite is true as well. If you decrease the volume, that pressure is going to go way up. Different scenario, let's say you have a gas in a container at a pressure of 2.6 atmospheres and a temperature of 285 Kelvin. Looks like we have pressure and temperature. What will happen to that pressure if we heat the container up to a higher temperature at 304 Kelvin? Go ahead and answer now. You should have said that pressure will also increase, according to Gay-Lussac's law. As those particles move faster and faster at the higher temperatures, they'll hit the walls of the container more often and cause a higher pressure. One more question for you here. Let's say you have a balloon filled with helium gas. It's got a volume of 3 liters, and it's at room temperature, 298 Kelvin. But you take that balloon, you put it in ice water, and you bring its temperature down to 273 Kelvin. If you decrease the temperature of the balloon, what will happen to the volume? Please answer this question now. According to Charles's law, as the temperature increases, volume increases as well. So if the temperature decreases, volume will also decrease. That balloon is going to shrink. So those were our early gas laws. Let's take a look at the ideal gas law. Remember, the formula for this is P times V equals N times R times T. It brings together all of the different gas properties, the pressure, the volume, the number of moles, this R that we'll talk about in a second, and temperature. This can be derived from experiments and theories in the lab, and it states the condition of an unchanging gas. It just says one point in time. What is the state of that gas? So how do we use this equation? Well, remember, P is pressure, V is volume, T is temperature, R is the number of moles of gas, N is the number of moles of gas, and R is a constant value called the ideal gas constant, and it always has a value of 0.0821. There are units with it. We won't deal with them in this class. So let's take a look at how to actually solve a problem using that ideal gas law. If we ask how many moles of N2 gas is required to fill a small room with a volume of 27,000 liters to a pressure of 0.98 atmospheres and a temperature of 298 Kelvin, first we would write down all the variables and we would list what we're looking for as a question mark. From the problem, I can pull all of this information directly from what's written. Next, I will write down the ideal gas law equation and plug in whatever values I know. So I put the equation right here, and then notice I plugged in 0.98 for pressure, 27,000 for volume, N I don't know, so I'll leave it alone. R is always 0.0821, and T is 298. The third step, multiply any numbers not connected to the variable. 0.98 times 27,000 is 26,460. I'll leave N alone because it's a letter. And then I'll multiply 0.0821 and 298 to get 24.47. And we'll rewrite the equation exactly as shown. Now our last step is to divide both sides by the number connected to the variable. If I do 26,460 divided by 24.47, I get 1081.32, and N remains on this right side. And that tells us there are 1081.32 moles in that balloon. Now let's have you try. You have a fire extinguisher filled with CO2 gas. The volume of that extinguisher is 2.1 liters, and the gas pressure is 3.2 atmospheres. There are 6.7 moles of gas in that canister. What is the only piece of information you are missing? You should have said that temperature was the only piece of information you were missing. That is the only thing not listed in the problem. And that's what we're going to solve for. So, how would you correctly set up the ideal gas law equation? Please do that now. You should have found that you had PV equals nRT, and after we plug in, we'd have 3.2 times 2.1 equals 6.7 times T times 0.0821. Next, perform the first step of the math equation. We have it perfectly set up here. How would you perform the first step? Write down your answer or record your answer on the EdPuzzle. You should have said that 3.2 times 2.1, you get 6.72 on this side, and 6.7 times 0.0821, you get 0.55 on this side, and T remains T. Now, please perform the last step of the math equation, trying to solve for temperature. How would you solve for temperature? You should have gotten, when you divided both sides by 0.55, 6.72 divided by 0.55 gets us 12.22. And that is the temperature of that fire extinguisher. And that is the Unit 4, Section 3 EdPuzzle.